Today, we are diving deep into the powerful mathematical engine that drives so much of modern finance. We're talking about multivariate calculus for trading. Welcome to Athena Quant. This is the core math that allows quants to navigate the incredibly complex world of financial markets. And it all really kicks off with one fundamental, almost impossible sounding question. I mean, think about it. You've got thousands of stocks, bonds, commodities, and an infinite number of ways to combine them. So how in the world do you find that single best portfolio? It honestly sounds like an impossible task, but this is exactly the kind of problem that multivariate calculus was born to solve. To get our heads around this, let's use a little analogy. I want you to imagine every single possible portfolio spread out across a vast, multidimensional landscape. The altitude at any given point could be, say, your Sharpe ratio. That's your return for every unit of risk you take. So your job becomes finding the absolute highest peak on that landscape. Or maybe you're looking for the lowest valley, which would represent the portfolio with the least possible risk. Okay, so if you're going to navigate this massive landscape, you're going to need a compass, right? Well, in calculus, that compass has a name, the gradient, and it's the first critical tool in our toolkit. So what is a gradient really? Well, it's a vector, which is just a fancy way of saying it's a list of numbers. Each number in that list corresponds to one of the assets in your portfolio. What it does is bundle up all the individual slopes, the partial derivatives, to point you in one single direction, the direction of the steepest, fastest climb. It literally tells you, hey, uphill is that way. And here's where this gets really powerful in the real world. If you calculate the gradient of your Sharpe ratio, it tells you precisely, step by step, how to make your portfolio better. It points to the exact assets you need to buy more of and which ones you need to sell to get the biggest bang for your buck in terms of improvement. Now, the math behind this is actually surprisingly beautiful. Take this formula, for example. The gradient of your portfolio's variance, which is just a measure of risk, is simply 2 times the covariance matrix, we call that sigma, multiplied by your current portfolio weights, W. That's it. And what does that formula actually give you? It turns this abstract math into an incredibly practical tool. That vector you get from 2 sigma W basically acts like a real-time risk dashboard. Every number in it tells you the marginal risk contribution of each asset. You can see instantly which holding is causing you the most pain. But a compass isn't enough. Just knowing which way is uphill doesn't tell you if you're about to walk off a cliff. You also need a map, something that shows you the shape of the terrain. And that brings us to our second tool, the Hessian matrix. The Hessian is a big grid of all the second derivatives. Now, if the gradient tells you the slope, like your speed, the Hessian tells you how that slope is changing, kind of like your acceleration. It describes the curvature. Is the ground curving up under your feet like you're in a big bowl, or is it curving down like you're on top of a dome? And this is a total game changer. For portfolio risk, the Hessian is just 2 times the covariance matrix. Sound familiar? Now, this matrix has a special property. It's positive definite. And all that means, in simple terms, is that the entire risk landscape is shaped like a perfect, smooth bowl. There are no tricky little false bottoms to get stuck in. There is one single global minimum. This is the mathematical guarantee that a unique minimum risk portfolio not only exists, but that we can actually find it. So, we've got our compass, the gradients. We've got our topographical map, the Hessian. Now, how do we actually make the climb to the top of the mountain? Well, let's compare 2 common ways to get there. First up is gradient descent. This one's super simple. You just pull out your compass, the gradient, find the uphill direction, and take one small step. Then you do it again, and again, and again, maybe thousands of times. It's exactly like hiking up a mountain in a dense fog. You can only see the ground right in front of you, so you just keep taking small, careful steps uphill. Now, contrast that with Newton's method. Here, you use both the compass and the map. Because you use the gradient and the Hessian, you understand the actual curvature of the landscape. You don't have to take tiny little steps anymore. You can calculate the single perfect jump that will land you right on the peak, often in just a few tries. It's like the fog has completely lifted. So if we put them side by side, it's pretty clear. You've got a classic trade-off. Gradient descent is simple. It doesn't need as much info, but boy, is it slow. Newton's method, on the other hand, uses that extra information from the Hessian to be incredibly fast and efficient. It just takes a bit more computational muscle to pull off. All right, this has been a fun trip through the theory, but let's bring it all back to reality. How does this abstract math actually get used by a professional quant to drive automated trading? Remember that beautiful, elegant formula for the risk gradient we saw? Well, here's what it actually looks like in the real world. It's a single, clean line of Python code. This right here is how profound mathematical ideas get turned into algorithms that manage billions of dollars every single day. So to wrap it all up, let's review our toolkit. We have the gradient, that's our compass, always pointing us in the direction of the fastest improvement. And we have the Hessian, that's our map, showing us the curvature of the landscape so we can find the smartest path to the solution. And I really want this to sink in. This isn't some dusty academic exercise. This stuff, multivariate calculus, is the living, breathing engine that finds optimal portfolios, that manages risk, and that powers the data-driven systematic trading strategies that truly define modern markets. So today, we've pulled back the curtain and found the calculus that's hiding right underneath portfolio optimization. And it really makes you wonder, doesn't it? What other invisible mathematical forces are out there, shaping the very markets you trade in every single day?